So let's continue. So you realize that looking at the second diagram, you guys do it. So I don't think I will draw it again. So looking at the second diagram, you realize that the north pole of the magnet was stationary. Now, when it was stationary, looking at the G or the galvanometer, there wasn't any deflection or there wasn't any further movement. And it's as a result of if there is no further movement, that means there's no current generated. So the current is said to be induced in the first one because there was a relative motion. Now, if the magnet is kept stationary inside the coil, the galvanometer shows no deflection. Now, if the magnet in the third one, you realize that if the magnet is withdrawn, looking at the diagram, then it means that the magnet was withdrawn from the coil. Then it indicates that, and the galvanometer indicated that, or there was a deflection in the opposite direction. So realize that I do the same. There was a deflection, but the first one, when the magnet was moving towards the coil, it was in this direction. That means there was an increment in current generation. Now, when it was stationary, that means there wasn't any current increment or decrement. Now here, when it is moved away from the coil, and that means there's also a deflection in the opposite direction. And that means the current keeps reducing. Let me put it that way. And so there's a deflection in the reversed or opposite direction. Basically, that's what it means. Now, when you're also to keep the solenoid constant, when you're also to keep the magnet constant, and you in turn rather start moving the solenoid closer to the magnet, you still get the same experiment. Now, after the experiment was made, he was able to ascertain the fact that number one, an EMF, which is an electromotive force, is induced in a coil whenever there is a relative motion between the coil and the magnet. So you realize that in the first one, when there was relative motion, that's when the current, the magnet was moved towards the coil, there was a current generation. As a result, you are saying that an electromotive force or a current has been induced. Now, number two, the conclusions that was made, number two, was that the magnitude of the induced EMF, the magnitude, that means the strength of the induced EMF, increases with increment. Increases in the relative motion of the magnet and the coil. So that means when there's an increment in the relative motion of both the coil and the magnet, then that means the strength or the magnitude of the induced EMF also increases. Are you getting it? So you realize that the induced EMF thrives on the relative motion between the coil and what do you call it? Here, the coil is the conductor and the magnets. Now, the third one is that the magnitude of the induced EMF depends on the strength of the magnet. So it also depends on the strength of the magnet. That means if the magnet has a bigger strength, then definitely the EMF that will be induced will also be very strong. Basically, that's what it means. So the first one conclusion he was able to make out of the experiment was that the EMF is induced in a coil, or the EMF induced in a coil whenever there's a relative motion between the coil and the magnet. According to experiment, that is when he was able to connect a solenoid to what do you call it? When he connected a solenoid to a galvanometer, and he brought a magnet closer to the solenoid. What happened is what he's concluding. And so we realized that when it was brought to when the magnet was brought closer or was moving towards the coil, there was a deflection in the galvanometer, which stipulated which showed that there was current generation. However, when it remained stationary, there wasn't any movement again, or there weren't any deflection again. And so that shows that when it is stationary, then that means there's no current generation, or there's no increment or decrement in current or induced EMF. Now, I also show that when the magnet is moved away from the coil, the current moves in the opposite direction. That means it moves in the negatives or in the reverse. And that means when it is moving, then that means it also moves in the reverse. Basically, that's what it means. And after this, he was able to conclude that an EMF is induced in a coil whenever there's a relative motion between the coil and the magnet. So every time there's a relative motion between the coil and the magnet, an EMF is induced. Number two, he was able to ascertain the fact that the magnitude of the induced EMF, that is the size of the induced EMF, normally increases with an increase in the relative motion. That means when the relative motion between the coil and the magnet is increased, then that means the magnitude of the EMF also increases. That means if you want to increase the size of the EMF, you have to increase the motion between, or the relative motion between the EMF, the magnet and the other one, what they call the coil. Now the third one, he was also able to ascertain the fact that the strength or the magnitude of the EMF also depends on the strength of the magnet, because the magnet is the main thing that is causing the generation of the current. And so that means before we can be able to get an increased or a bigger size or a bigger magnitude of what do you call it, of an induced EMF, then that means you would have to get a substantial magnet or a big magnet or something. And so it normally depends on the strength of the magnet. So the strength of the magnet plays a bigger role in it. And so the magnitude of the induced EMF depends on the strength of the magnet. It also depends on the number of the coils. We studied this last week. It also depends on the number of the coils or turns of the coil, and also the presence of the soft iron core inside the coil and the large area of the coil. So it depends on all these factors. So it depends on the strength of the magnet. It also depends on the turns, number of turns of the coil, how many times the coil is turned. And definitely the coil is turned around, we have that inner core in it. So it also depends on the presence of the inner core, the soft iron core in it. The soft iron core is where the current is generated. That is it. It also depends on that. And also the large area of the coil. So basically that is it. That's what we've been able to ascertain according to Faraday's experiment. Now he further said that when you have an induced EMF in a straight conductor, an induced EMF in a straight conductor, an induced EMF, induced EMF in a straight conductor. Induced EMF in a straight conductor. So an EMF can be induced in a straight conductor when it moves in a magnetic field in such a way that it cuts the lines of the force of the field. So it can only happen when it is placed in a magnetic field and it's positioned in such a way that the conductor cuts or is perpendicular, in other words, perpendicular to the lines of the magnetic force or the lines of magnetic force. And so that is basically what it means. So the maximum EMF is obtained when the conductor moves, or when the conductor moves perpendicular to the lines of the magnetic force. And so when the conductor moves, we are talking about relative motion here. So when it moves perpendicular to the lines of the magnetic force of lines, or the lines of the magnetic field, then we are saying that we are going to get an increased EMF generation. However, the EMF will be zero when the conductor moves parallel to the field. This is already explained it. So when the conductor moves parallel to that of the field, so for instance, if this is the field and the conductor moves parallel, it is positioned parallel to the field, and that means there won't be any current generation. We studied this when we were doing the talk. However, when it is perpendicular to the fields, the lines of the force, they are imaginary. So when it is positioned to be perpendicular to that imaginary lines, which you call the magnetic lines of force, then we are saying that there will be an increment in the EMF in that. Now this has been grouped, or this has been this principle or this theory has been written or has been coined into what you call it, a rule, and that we call the Fleming's right hand rule. Realize that we study the Fleming's left hand rule. Here we are going to talk about the Fleming's right hand rule under induction or electromagnetic induction. Now, the direction of the induced EMF is determined by the Fleming's right hand rule. And so according to the Fleming's right hand rule, it's basically like the same, the first one, just that you realize that the first one we are talking about conventional current, but here we'll be talking about induced current. The first one we are talking about conventional current, but here we are talking about induced current. Here we are talking about induced current. So we state the Fleming's right hand rule that as the Fleming's right hand rule states that if the first two fingers, basically the same thing, if the first two fingers and the thumb of the right hand are held at right angle triangles, so are held at right angles to each other. So there's my right hand, so that is it. There's my first two fingers, and there's it. So just as we did the other time, basically like the same thing. So there's this, and there's it, and there's this. Then you're trying to say that the forefinger points in the direction of the field. So this one points in the direction of the magnetic field. And according to what I just explained, when a magnetic field is perpendicular to that of the conductor, then that means there will be an induced current. So let me just explain it again. And so states that if the first two fingers and the thumb of the right hand are held at right angles to each other, with the forefinger in the direction of the field and the thumb is in the direction of the motion. So this thumb is in the direction of the motion. So this is the movement, the direction of the movement, or the motion of what we call the conductor in this case. So we said that when the conductor moves perpendicular to this, to the magnetic field, so this is the magnetic field, and this is the motion, the relative motion between the conductor and what do you call it, the magnetic field. Then the second finger points in the direction of the induced current. So this one will point in the direction of the induced current. So this one points in the direction of the induced current. That's what it means. And so I'll say it again. If the first two fingers and the thumb of the right hand are held at right angles, then we are saying that the forefinger points in the direction of the field. So this one will point in the direction of the field. Then before current can be induced, the motion or the movement of the conductor should be perpendicular. So then that means this is perpendicular. So this one, the thumb which is perpendicular moves in the direction of the motion. Then when these two happen, then we can have an induced EMF. That means an injected EMF. And so then we can talk about it. The second one, which you call the direction of the induced current. That is it. Any question? Any question? So with the first one, we are talking about conventional current, which is the Fleming's left-hand rule. But here we are talking about induced current. Here we are talking about induced current. We're talking about induced current. Now, let's consider some laws of electromagnetic induction. Our time it dropped. 2013 it dropped. Now, the first law we are going to consider is the Faraday's law. You quote it as it is. You don't add some, you don't take some, because it's a law. So I'm stating it. Faraday's law. Let me change the color and you can write. I'll go to so Faraday's law. There's there's apostrophe here. Faraday's law. Now, the Faraday law states that whenever there's a change in magnetic flux, it states that whenever there's a change in magnetic flux, whenever there is a change in magnetic flux, whenever there's a change in magnetic flux, or lines of force, or lines of force, linked This one is the proportionality sign. Let me just. I hope you're all writing. So flux linkage or magnetic flux, that is measured in Weber. Is equal to time. Measured in second. This is a negative. When we this, and the negative will be taken away, so don't worry. So total flux linkage. When you finish, you let me know so that this thing. So the Faraday law states that whenever there's a change in a magnetic flux or lines of force linked with the current, linked with the circuit, an EMF is induced. So whenever there's a change in magnetic flux or lines of force, an EMF is induced, the strength of which is proportional to the rate of the change of the magnetic flux or line. So of the magnetic flux, yes, flux. Of the magnetic flux or lines of force producing it. So it just simply means that in a field, anytime there's a change in magnetic flux, an EMF is induced. That means there's an added on of an EMF, or an EMF is induced. Then induced is an English word. An EMF is induced. So that is it. And the strength is proportional. The strength is proportional to the rate of the change of the magnet. So the rate at which the magnetic lines of force is changed is proportional to the strength. So that means if it is changed well, then that means the strength will also increase. On the other hand, when the change is in the negative direction, then that means the strength will also be reduced. Basically, that's what it means. And so it's proportional to the change of the magnetic lines of force. And so when the magnetic lines of force is plenty, then that means the strength will be higher. Now, when the magnetic lines of force is very small, then that means the magnetic, that means, what do you call it? That means there'll be a reduction, or the induced EMF will be reduced. Basically, that's what it means. And I know when we talk of the magnetic lines of force, you know what we are talking about. The imaginary lines of force that represent a magnetic field. And you bear with me that we said the higher the number of lines of force, the greater the strength of the force. The lesser the strength of what we call it, the magnetic field. So this one, Faraday is trying to say that whenever there's a change, that means when there's a change in magnetic lines of force, that means when you add some, there'll be a change. Now, when there's a change, then that means it will affect, what do you call it, the induced EMF, or there'll be an induced EMF. So the more you add, the more there'll be an induced EMF. The more it induces current or electromotive force. On the other hand, when it is reduced, definitely there'll also be a reduction. And so there'll be a change. So now, mathematically, we are saying that E, which is the induced EMF, is equal to the change, the negative of the magnetic flux with respect to time. So the rate at which the magnetic flux changes. That is it. That's what we are trying to say. Now, the magnetic flux is measured in Webers. T is measured in time, and E is the electromotive force, which is measured in volts. Now, by definition, you bear with me that the Weber is the magnetic flux through a coil of 1 turn. And so the Weber, 1 Weber is a magnetic flux through a coil of 1 turn. That is when it makes 1 turn. So before you can be able to get the total number of turns it makes, then that means you have to multiply it by n, by the number of turns. And so the number of turns we introduce in the n, and that takes that away, or that takes away the negative. So we are going to get E is equal to the n psi all over the T, where the psi is the total flux linkage. The total flux linkage. And so by definition, the Weber is the magnetic flux through a coil of 1 turn, which when reduced to 0 in 1 second, induce an EMF of 1 volt in the coil. So when it is reduced to a volt of 1, when it is reduced to 0 in 1 second, there will be an induced of 1 volt in a coil. Therefore, K is equal to 1. And hence, for a coil of n turns, this is what you are going. So when the question gives you that for a coil of so and so turns, then that means you have to introduce the n. Then you come and use this formula. So I think that will be the final formula. This will be the final formula. Now from here we look at the last law we'll be looking at. The Lenz law. Lenz law. Lenz law. The Lenz law. The Lenz law. Now the Lenz law states that the direction of the induced EMF is such as to always oppose the change in magnetic flux that causes the EMF. So the direction of the induced EMF. So after this, we further on, after this law, we further on to look at the Lenz law, which is the law number 2, and the laws of electromagnetic induction. And so, which we call the Lenz law. Now the Lenz law states that the direction of the induced EMF, the direction of the induced EMF is such as to always oppose. So the direction of the induced EMF, the direction of the induced EMF, the direction of the induced EMF is such as to always oppose the change in magnetic flux. So that means the direction of the induced EMF always opposes the change in magnetic flux that causes the EMF. And so the direction of the EMF, induced EMF, is such as always oppose the change in magnetic flux that causes the EMF. And because it is opposite, that's why we bring the negative. And so this one to E is equal to is still the same as this one now. This one. Mathematically, still the same thing. That's why we bring the negative here. So the Lenz law to mathematically, this is how it means. And so the change in this is said to oppose this one. the induced EMF. So the direction of this opposes this one. So under the Lenz law too, you can write mathematically this one. And so the negative expresses the Lenz law. The negative expresses the Lenz law, and the Lenz is Lenz. The negative expresses the Lenz law. That means, according to the Lenz law, the direction of the induced EMF is such as to always oppose. So because there's an opposition, that is why we equate it to a minus d. Minus d. Is it the psi all over the t? Minus the psi all over the t. So let's humbly take note of this. Let's humbly take note of this. Let's humbly take note of this. We have about 10 minutes to go. Are you done writing? Are you done writing? Any question to please?
Yes, so, sir, I done right.
Okay. Did you also write the Lenz law? I stated it. Now, when you have a metallic sheet, when a metallic sheet swings in a magnetic field, when a metallic sheet swings in a magnetic field, the movement of a sheet is soon brought to rest. Now, when a metallic sheet swings in a magnetic field, that means when you place a metallic sheet in a magnetic field, it swings. It swings. Now, when the movement of the sheet is soon brought to rest, it is due to, or let me put it this way, when a metallic sheet swings in a magnetic field, the movement of a sheet is normally soon brought to rest, or it will definitely be come to rest. Now, this is due to, and it is as a result of the induced EMF in the sheet, due to its motion cutting across the lines of the magnetic field. And so because the sheet, which is the conductor, the sheet which serves as a conductor, cuts or moves perpendicular to that of the what do you call it, to that of the magnetic field. That's why there's that swinging. So it is normally due to the current induced in the sheet, and the current which is induced in the sheet comes as a result of the motion cutting across the lines of the magnetic fields. That is the motion of the swinging motion cutting across the magnetic field. And now, to curb this error or this thing, we introduce something we call lamination. Lamination, where gaps are brought in between the sheet and so on and so forth. Now, according to Lenz law, an EMF is induced in the sheet in such a direction as to oppose the motion of the sheet. And so the induced current opposes the motion of this thing, and that brings it to rest. And so when it is swinging in the magnetic field, an induced current opposes its movement. Now, when it opposes its movement, it brings it to rest. It brings it to rest. Now, the induced current in the sheet arising from the induced EMF is called eddy current. And so that one, the induced current in the sheet is what we call the eddy current. So anywhere we see eddy current is the induced current in the sheet, which is as a result of the induced electromotive force. So the induced current in the sheet arising from the induced EMF is called eddy current. The eddy is EDDY current. EDDY current. And this eddy current normally can be minimized by laminating the metallic sheet. Now, when we talk of the lamination, we are trying to say that producing gaps in the sheet. And since the current cannot flow across these gaps, when you produce gaps in the sheet, current cannot flow across the gaps. As a result, the eddy current is now reduced. That means the movement and so on and so forth will be reduced. That's what it means. Please.
Sir.
Talk to me.
Please state the eddy current again.
So the eddy current is the induced current in the sheet arising from the induced EMF. The induced current in the sheet arising from the induced EMF is called eddy current.
Thank you.
Okay. Now, when we get to this thing, we also have some forms of what do you call it? electromagnetic induction. Now we have the self-induction and we have the mutual induction. With the mutual induction, we are going to talk about having the primary coil and the secondary coil. When we get to transformers, you understand it better. Whereby the current which is induced in the primary coil as a result affects or is also injected or affects what we call the current which is induced what we call in the secondary coil. So the current in the first vessel, which is the primary coil, gets induced or is passed on to the primary coil, and so it's passed on to the secondary coil. And so if you have the secondary coil, which is the innermost coil, then now it affects or it is passed on to the secondary coil. So now the secondary coil becomes induced. That we call it mutual induction. So the current can also be induced by use of another current. And so to do this, the turns of the insulated wire are wound into a coil, which can be introduced in the ladder coil. So the ladder coil here now becomes the secondary coil. The smaller coil is called the primary coil, and the larger coil is the secondary coil. So let me just give you an example so that we go. And the self, that one, it generates on its own. This they are all reading, so I wouldn't want to spend much time. I've been talking since morning. Maybe so. So this a metallic iron core, and it's also connected to the primary distance. There's another one, but this one is larger. And they are all wounded around with coils of wire or metallic distance. So that is it. And we also have, this is a primary coil. Then we are going to, which is connected to, this is your resistor here, connected to a cell. So when the primary coil is introduced in the secondary coil, it causes a momentary current to flow in the primary coil by tapping the key. And so when you tap this key, current is generated. That means you what do you call it? When you close the circuit, current will definitely be generated. Like when the current is generated, it is just passed on to the secondary coil, and that is what we call. So the current gotten from here is induced into the secondary coil. That's what we call the mutual induction. I don't want to talk too much about it. That's what we call the mutual induction. And we have the self-induction. That is when the circuit contain the switch and the coil is, when it self-induces. I don't know how to explain the self-induction. Self-induced EMF tends to increase or something. So when current is generated on its own, not using this diagram, basically that is what it means. So that is it. We have so kindly go and read what we call the use of go and do the reading of self-induction and the mutual induction. Read more about it. They are all theory, so go and look at its operation or how it works. When you don't understand anything, come and ask me, I'll explain it to you. We are in the second week, so please let's do the needful, I beg. Next week we are doing alternating current, and I need everyone to be in class. Remember last year your sisters couldn't even finish, and so I want to definitely finish the alternating current for you guys. And this one is basically, they're all maths. So you have to be around, and it's very simple, but I'll just have to explain it. You get it well. So please remind your parents so that they do the needful. Have a wonderful day. I'm tired. Have a wonderful day.